Well, hello guys. I know it's been a while, but we're back. And today we're doing another reference video. We're going to be talking about gates and triggers, and specifically how to handle gates and trigger signals coming out of our microcontroller so that we can use them in another Eurorack project. So let's get to it. Today's goals are really simple. We just kind of need to get a little bit of an understanding of gates and triggers, which should not be very difficult because we covered a lot of that stuff in the last video. Then we're going to talk about some schematics that we can use. We'll do some simple code and make some blinky lights. Okay? All right, so first off, what are we talking about? So gates, triggers, we're talking about today. Control voltage, another output type. We're not going to be talking about that today. That really deserves its own topic, so we're going to save that for a future video. LEDs, we will be talking about that today because LEDs, the way we drive gates and triggers is exactly the same as how we drive LEDs, so why not cover that, right? LED displays, though, that's a totally different topic, so we'll wait on that one as well. MIDI, we'll probably cover in the next video. Part of the reason why I wanted to break this up is because some of those topics can be quite deep, and so we're gonna take it step by step. So let's start with the easiest part, right? LEDs. When we're talking about LEDs, there are some things that we should consider. First thing is that LED brightness is determined by how much current it goes through the LED. And in order to light up an LED, we need to have a current limiting resistor. If you just try to wire up an LED directly to a pin, it won't work. Each LED is going to need about 0.02 amps or 20 milliamps to light up. To calculate the brightness, we can just use Ohm's law. Different color LEDs will have a slightly different voltage drop, but as long as you stick with some numbers that are close to it, I think you should be fine. A lot of this stuff, it doesn't have to be an exact science, it just needs to be something close to it. All right, what I have in this slide is just a few different possible combinations that we could use. If you have an LED connecting to a 12-volt source, then a 500 ohm will give you a really bright LED, while a 1K is going to give you a slightly dimmer LED. And as you can tell here, 5 volts versus 3.3 volts is going to be lower resistance that we need, right? Because we are starting from a lower voltage, Ohm's law, right? Here's an example of how you would wire the LEDs in series. Now, just to keep under, something to consider is that when you drive these, all of these are going to be driven at the same time, right? So if that's what you want to do, great. But if you want them to be independent, have independent signals, then you want to wire it to a separate pin. If you were to wire a LED directly to the Eurorack power rail, then, here is 12 volts. So you could still use this knowledge for that. If you have an Arduino, most of them, like an Uno, that's 5 volts that each pin can source. So you can use this calculation in the middle. And then, as I was mentioning, that different resistor values will have different brightness. So the larger the resistance, the less bright the LED will be. What I've discovered is that the LEDs are a little too bright for my taste when I do the calculation to what its optimal brightness should be. So I like them a little bit dimmer. So I tend to go with higher value resistors for my projects. There's plenty of information on this on the internet, so I'm not going to go anymore on this. Let's go ahead and move on to the next topic. Okay, so here are a few things to consider when working with triggers and gates. The first one is voltage level shifting. So in the Eurorack world, we expect triggers and gates to be somewhere between 5 and 10 volts. It could even be a little bit lower, but we're going to assume 5 volts because 5 volts is likely going to work everywhere. However, our microcontroller is operating at 3.3 volts. And so in order to get it to that level, we're going to have to amplify it. Okay, so the next thing we're going to do is we're going to condition the signal. And this mainly applies for, microcontrollers that can drive 5 volts. So say, for example, if we were using an Arduino, the pins can drive 5 volts. In that case, all we're going to do is we're going to use some diode clamps, just like we did the last time. And that's going to make sure that your signal stays within whatever you clamp it with. So ground and 5 volts in our case. Okay. There is one gotcha there. Depending on the microcontroller that you have, you may not be able to have enough current to drive something down the line, another module, for example. The microcontroller we're working with today, not only does it run on 3.3 volts, but each pin can only source about 6 milliamps of current. And that might be enough to avoid any issues with, our pins not being able to drive anything. We're going to make sure that we buffer the signals so that the signal can have its own current source. And so that's the next bullet point here, right? We're going to use buffers to make sure that that we have a dedicated current for those output jacks. Now, there's another added benefit that the buffering gives us, and that is that it provides a certain isolation between the circuit. Now, of course, it's still electrically connected, right? We still are sharing a ground and pin, so it's not really isolation that we're talking about. If we really want true isolation, then we would use something like an octocoupler. But for this situation, we don't really need it. We might use it when we start talking about MIDI. And so, we'll talk about optical isolation there. But all we're really talking about here with buffering, it's not really isolation. Maybe that's the wrong word. It's more a way to decouple both circuits. Okay. And that will do one additional thing, which is that it will give us some protection for the pins, and we'll cover that in a minute as we look at some of the examples. Okay, so here is the first one, and in this example, we are driving a jack directly from the pin. We're not buffering it. Because we're not buffering it, we are putting a diode clamp, so that's going to ensure that our signals that we push out are never going to be above 5 volts. As well as if we were to put something, plug in something else from reverse, the max that we would see is 5 volts. And because we are putting this resistor right here, that will limit the current that the pin sees. So if we plug an output into our output, we're not going to damage the board that way, okay? This might not be the best way to deal with a trigger or gate output for the reason that I just talked about, right? This does not have its own current source, so it might not be enough for what we intend to use it for. So instead, if it's a 5 volt pin, we can buffer it with an op-amp, and all we have to do is just put it in a buffer configuration like this. This current limiting resistor here is 1K. That is what is expected in the Eurorack environment. So that's how we arrive at that value. So for a 3.3 volt pin, instead of putting it in a buffer configuration, we'd put it as a non-inverting amplifier. And this resistor configuration here, these values here will give you exactly what we need to raise this from 3.3 volts to just a little bit over 5 volts, which would be more than capable for gates and triggers. Here's another way that we can do this. We can also do this just by using an NPN transistor and a couple of resistors here. The only gotcha here is that this is an inverting, acting more like an inverting buffer. So when the base here of the transistor is at 0 volts, no current will get let through, and so everything that the output jack sees is going to come from the rail here, which is at 5 volts. Now, when we have a positive voltage on the pin, this then will start conducting from the collector to the emitter. And because of that, this is going to have a straight through connection to ground. Current is going to flow in this direction. So when we plug something over here, what will be shown at the output jack is going to be ground or 0 volts. So positive here, 0 volts out. Positive 0 volts here, positive signal out, right? So it's an inverting buffer. So, and you know, the fact that it's an inverting buffer, it's actually has very little consequence here, because all we have to do is just invert it in code and then we're good to go. Let's move over to VSCode and let's take a look at some sample code. So right here, what I have is it's just a very simple. I'm configuring 3 pins. We're gonna wire up PB12 and 13 to 2 LEDs, and I am going to use two different sizes resistors just to see if we can notice the difference in brightness. And then we're gonna configure PA11. We're going to pass that through an op-amp, and then we're going to measure some voltages at the end. And that is it. This thing is going to blink every, I think, 5 seconds. We're going to leave it, so 5 seconds on, 5 seconds off. First things first. Let's turn this on. Can we see? Yeah, we can see. So right now it's like 8 millivolts. There's nothing going on in there, right? So that's pretty much 0 volts. Let's go ahead and flash the microcontroller. So one thing to note, I am powering this microcontroller from an external voltage source. This actually provides 5 volts, which is what I'm using over here to drive the microcontroller. And I am taking 12 volts for the op-amp. Okay, so just because I wanted to illustrate this, right? So if I was doing this in a project, I would need to get a regulator to regulate from 12 volts down to 5 volts. Unless, you know, you have a power source that can give you all 3, then you don't need to do that. But 5 volts go into this rail, 12 volts on this rail, and the only thing that we're using 12 volts for is this TLO72 op-amp, and 5 volts is powering up the microcontroller, and that's about it. The LEDs are going to be driven from these 2 pins. So I'm using PB12 and PB13. These 2 pins here are going to be our LEDs, and then PA11 is what I'm going to be driving the gate out of. Okay, so let's take a look here and let's flash this. One thing to note, because I am powering this from an external power source, my ST-Link, I only have ground and the 2 signal pins connected. I left the 3.3 volts unplugged. Okay, we definitely don't want to send power from an external source and power from the USB at the same time, as that could damage the microcontroller. Okay, so let's go ahead and send this to the microcontroller, and we should see this start to blink. There we go. It's blinking. And I left the blink duration longer because I wanted to see if you guys could notice that one of them is lighter than the other, right? So this right here, I think it's a 68 ohm resistor, and this is a 150 ohm resistor. And it's, I mean, the 150 ohm resistor is still bright, it's still pretty bright, but it's definitely a lot, you know, it's dimmer than its partner over here, which is a lot brighter, right? So I personally rather have the slightly dimmer lights because they kind of hurt my eyes, but you know, it's a matter of choice. And then over here, we see, along with the LEDs, that when these light up, we're getting a little bit over 5 volts. And then it goes down to millivolts, which is going to be interpreted as a low gate, right? So 5 volts and then down. So yeah, there you have it. That's really all there is to driving gates and triggers, right? The main difference between a gate and a trigger is going to be the duration of how long the signal stays high. I think, you know, again, this is going to be depending on each manufacturer, right? But around 10 to 20 milliseconds is typically the duration of a trigger signal. So, you know, we would just account for that in our code. So today we learned that LEDs, driving LEDs out of microcontrollers is super easy. We also learned that gates and triggers are actually also quite easy, right? And we purposely left the other topics of CV and audio because they are not as easy, but we will cover them in a later video, so that's okay. We also talked about some of the main concerns when we are driving signals out of our microcontroller, right? So main concerns are we want to protect our microcontroller from incoming signals. So something that can sink current will protect the pins. And then we also want to make sure that we provide a dedicated current source for the signals going out. So not much to it, but that's it. We should now have enough knowledge to start building at least a module. So that's what we're going to do in the next few videos. We might cover one more topic before we do that, or maybe we'll combine it into the two. But yes, and so stay tuned, definitely stay tuned, because we are going to be putting this to exercise. PCBWay has offered to sponsor another video, so definitely excited about that. If you don't know who PCBWay is, check the links in the description. Go check them out. They are a PCB board manufacturer. And in the next video or so, we are going to be making another module, and we're going to get it professionally done. Okay? We're going to use the knowledge we've accumulated so far, and we'll do something fun with it. Okay, cool. Okay, so this has been Gates and Triggers, Microcontrollers, and we'll see you guys next time.